Welcome to my talk about the maximal information problem and new insights about gathering and chain formation. My name is Jannik Castenow, and this is a joint research with Thorsten Götte, Till Knollmann, and Friedhelm Meyer of the Heide, all from Paderborn University. In our research, we consider robots with limited visibility. So in our understanding, robots are point-shaped and located in the Euclidean plane. Each robot is able to observe other robots only up to a constant distance. Usually you would model this as a unit disk, so you say a robot Ri can observe all other robots within a disk of radius 1 around itself. Typical formation tasks for robots with limited visibility often have a contraction property. So the positions of the robots have to be brought closer together. A very famous example is the gathering problem, where the initially scattered robots have to gather at a single, not predefined position. Another problem that falls into this category is the chain formation problem. Here we have a chain of robots. The two outer robots at the end of the chain are stationary and do not move. All inner robots have exactly two neighbors. These neighbors are predefined and fixed. So robots always can identify their two neighbors. Due to the limited visibility, it is always ensured, or the algorithms always have to ensure, that the distance between a robot and its neighbors is at most 1. Now, the goal of the chain formation problem is to reduce the length of the chain as much as possible. So to arrange the robots on the straight line between the two stationary outer robots. That's a goal here. On the contrary, we have the class of expansion problems, where the robots somehow have to spread out and close a large area or maximize something. One example with very few results under strong assumptions currently is the uniform circle formation problem, where we have an initial set of robots that have to be arranged on the vertices of a regular polygon with side length equal to the visibility range. And another example, and the main inspiration for our work here, is the max chain formation problem. Max chain formation problem is very related to chain formation, with the difference that the outer robots have the ability to move here. So these two aren't stationary anymore. Now the goal changes to maximizing the distance between the two stationary outer robots. That is to arrange the robots on a straight line of length n-1, connecting the two endpoints of the chain. In this work, we study the max line formation problem, which is inspired by the max chain formation problem, but the difference is that we don't have a chain. So we have a swarm of robots, and we want to arrange the robots on a straight line of length n-1. But here we have classical visibility models. So we say again, a robot can observe all other robots up to a constant distance. This also implies that there aren't two somehow special robots that form the ends of the line. Also, this role isn't predefined. So throughout the execution of an algorithm, two robots have to identify themselves as being endpoints of the final line. Okay, that's a problem we want to solve. We start with an impossibility result here saying, okay, in the OBLOT model with circular viewing ranges, this problem is impossible to solve. What is the OBLOT model? That's somehow the standard robot model, having all these features you might know, that the robots are anonymous, autonomous, homogeneous, and so on. And most importantly, the robots are oblivious and silent. So the robots don't have any memory of the past, and the robots do not communicate. So they simply look, compute, and move. And that's also how time is defined. So we have we have synchronized look, compute, move cycles in this research. So in look, robot takes a snapshot of its environment. In compute, it computes a target point and moves there finally during move. And these cycles are synchronized among all robots. So there are two different time models. Then we have fully synchronous robots and semi-synchronous robots. Fully synchronous robots, that every robot participates in every cycle. Semi-synchronous means that the cycles are still synchronized, but only a subset of all robots participates in a cycle, and we don't know this subset. Okay, so this was a small model excursion, but now under the OBLOT model with circular viewing ranges. So as I defined earlier, that if you say a robot can observe all other robots within distance 1 around itself, then it's impossible to solve. And how to see this impossibility? We start with a configuration of 3 robots and assume there is an algorithm M that solves this problem. This algorithm M would transform the 3 robots here to the left into a straight line of length 2. So for example, the robots are finally arranged like this: R1, R2, and R3. Then we define the second configuration of these 7 robots to the right. And the second configuration is parallel to the final configuration of the 3 robots. And this configuration is an H configuration. So the robots are positioned like the letter H. So the robot R4 can only observe R5, R5 can observe R4, R6, and R7, R7 can observe R5 and R9, R9 can observe R8, R7, and R10, and R8 can only see R9, and R10 can only see R9 as well. Okay, so basically we have 2 legs, which look like the final configuration here, and we have 1 robot connecting these 2 legs. Now the algorithm M cannot distinguish the robot R4 in this configuration from the robot R1 in the final configuration to the left, because it looks exactly the same. There is 1 robot and the other robot is in distance 1 below of the robot. This implies that R4 wouldn't move. With the same arguments, R8 cannot move. And with similar arguments for R3, also the robots R6 and R10 cannot move. So we already have 4 robots which are not allowed to move, or which can't move based on the definition of M. Additionally, R5 and R9 now can't move, because no matter where they move, they will lose the connectivity to either R4, R6, or even to both of them. So as an example for R5. And as soon as we lose connectivity, we can't deterministically ensure that the robots will reconnect again. So we always have to maintain connectivity. So also R5 and R9 cannot move, and as a consequence, also R7 cannot move, or at least make no progress, because no matter where R7 moves, it also loses the connectivity. And hence, no robot can move in the second configuration. This holds even for fully synchronous robots with an agreement on both axes of the local coordinate systems. So even if the robots have a common understanding of north, south, east, and west, they cannot solve this problem. Okay, so that's an impossibility result. On the positive side, we can show that with enhancing the local views of the robot slightly, we can potentially solve the problem. At least we can design an algorithm which converges to the optimal configuration. And how do we enhance the local views of the robots? So first of all, we assume a 1-axis agreement. So the coordinate systems of all robots are commonly aligned, and the robots have a common understanding of right and left, while up and down can be inverted from robot to robot. Now, each robot can observe all other robots with an axis-aligned square of side length 2 centered at its own position. So on the left, it can only observe all in the circle, and here it can observe all in the slightly larger square. Especially in the corners of this square, the robots gain, or at the boundary of the square, the robots gain more visibility. And now the problem becomes solvable, or at least we can design convergence algorithm, because still for R4, R6, R8, and R10, the same arguments hold. They wouldn't move in this configuration. But R5 and R9 are now allowed to move because they can move horizontally without losing the connectivity to their neighbors. For example, R9 can move to the left towards R7 without losing connectivity to R8 and R10, because still the entire line segment between R9 and R7 is contained in the square viewing range of R8 and in the square viewing range of R10. So now we gain the ability to move here. Algorithmically now I will introduce an algorithm converging to the optimal configuration under the OBLOT model. We consider robots, again, that agree on one axis of their local coordinate system, so the robots have a common understanding of left and right. The algorithm is now basically designed to work in two phases. In the first phase, we arrange the robots on a straight line parallel to the y-axis, and in the second phase, we stretch this line properly. Due to the limited visibility, robots can, of course, not distinguish these two phases globally. So they always have to act based upon their local view. So if a local configuration looks like this, so not all robots are located on the same line parallel to the y-axis, then a robot moves according to phase one of the algorithm. If the configuration looks like here, so the robots are already aligned on a line parallel to the y-axis, then it moves according to the phase two algorithm. In phase one, all robots move to the left. Well, basically not all robots at the same time. We say if a robot is rightmost in its local neighborhood, then it moves horizontally to the x coordinate of its leftmost neighbor. So here the robot Ri observes the position of its leftmost neighbor down here, and now moves horizontally to the x coordinate of this neighbor. That's the main idea. Of course, we have to take care about a few things. Most importantly, we have to avoid collisions. As soon as two robots collide, so they move to the same position, we cannot deterministically separate these two robots anymore. That's why we have to avoid collisions. So, of course, we have to assume initially all robots are located at distinct positions, and then we have to design the movement such that no collisions occur. What can we do here? For example, in this figure, the position where Ri wants to move to, this position is already occupied. In this situation, it does a slight movement to upwards from its local view. So again, robots don't know up and down, so it might also be the other direction. While moving upwards, again, has to avoid new collisions, because there might be a robot wanting to move to this position, and that has to be avoided. So it moves basically a third times to the position of its closest neighbor top with a y coordinate above itself. Okay, that's the main idea here. Moving to the left, only if robots are rightmost of the neighborhood without creating collisions. In the second phase, we make use of the max go to the middle algorithm, which has been designed for max chain formation. Because the configuration here can be more or less interpreted as a chain, because robots have somehow predefined neighborhoods, which are their closest neighbor above and the closest neighbor below. The algorithm works as follows. Inner robots, which are not at the end of the line, move to the midpoint between the closest neighbor above and the closest neighbor below. So go to the middle. Robots at the end of the line stretch the line as follows. This robot imagines a virtual robot in opposite direction of its single neighbor. So here opposite in distance 1, it assumes there is a virtual robot, and then it moves to the midpoint between the virtual robot and its real neighbor. And by this movement, it moves upwards and stretches the chain. What we can prove now is that after O of n squared epochs, all robots have joined phase 2. An epoch is the shortest number of rounds, such that each robot has executed its LCM cycle at least once, such that after O of n squared epochs, finally the robots are located on the same line. The second phase can be analyzed by a nice analogon or a nice relation to time inhomogeneous Markov chains. So here we look at the vector representation. So we always look at the vectors connecting two neighbors in the chain. So the vector v1 is the neighbor from the virtual robot to the first robot in the chain. And this is always the vector -1 in this drawing here. And then the next vector pointing to the next robot below is called v2, and then we have v3 and so on. And the last vector again points to the virtual robot is again the -1 vector. And now depending on the movements, which robots are active and so on, we always get a structure which is stochastic. So if we would if we would write down the behavior of these vectors as a matrix vector product, we would have a stochastic matrix. And this matrix can be interpreted as the transition matrix of a Markov chain with two absorbing states, because these vectors here never change, they are always the same. And because in every round, another subset of robots might be active, these matrices are time inhomogeneous. So in every round, they might look slightly different, but they are always stochastic. And yeah, now how to analyze this, just a rough idea is to define such a potential here. The potential is the difference of a vector to these two fixed vectors, to the -1 vectors squared, and the sum over all these squared distances or differences to these vectors. And yeah, the analysis then is quite technical, but with this knowledge, one can prove that after n squared log n divided by epsilon epochs, the line has a length of at least 1 minus epsilon times n minus 1, meaning we have reached a 1 minus epsilon approximation. Okay, starting from the OBLOT algorithm here, we have two research questions. First of all, can we design faster algorithms? And secondly, is it possible to solve max line formation exactly and not only converge to the optimal configuration? The answer is yes, but under stronger assumptions. So if we consider luminous robots and the fully synchronous time model, this is possible. So luminous means robots are not completely oblivious and silent anymore, but they gain locally visible memory. So each robot has a light with a certain number of colors, usually bounded by a constant. And if it activates the red light or the red color in its light, then this can be seen by nearby robots, and it can also be seen by itself. So it can store a constant number of bits for itself and can also communicate a constant number of bits to its neighbors. And we are fully synchronous robots, so now every robot participates in every round. So first of all, we need a speed up of the first phase. Actually, we don't need lights for this speed up, so this speed up can also be implemented in the OBLOT algorithm, but because the second phase was very slow in the OBLOT algorithm, it wasn't necessary for the asymptotic runtime. Okay, so how to obtain a speed up? Just a rough idea. Not only robots that are rightmost in their neighborhood move to the left, but all robots continuously move to the left. Now the collision avoidance is a little bit more complicated, because now multiple robots might move to the same position. So for example, these two robots might want to move to this position here. And then based on their ordering along the x-axis, which is unique because they have a common understanding of left and right, they will identify a new target position. Okay, so all robots simultaneously move to the left. The second phase now makes use of the locally visible lights. And the idea is to start a sequential movements every 3 rounds. Sequential movements or every 3 rounds can be counted with a simple counter. So every robot counts 0, 1, 2, 0, 1, 2, 0, 1, 2. This can be done with a constant number of colors in the light of each robot. Then whenever the light is currently 2, in the next round, this robot will have an active light. So in this round, the robot will activate its light such that it observes in the next round that itself has this light. And only robots having such a light will move. And now the movement is quite simple. This robot moves in distance 1 to its neighbors. to its single neighbor. So it creates a vector of length 1 in this line. And afterwards, the next robot moves, and then the next robot moves, and so on. That's the sequential movement, but every 3 rounds a new movement starts, so we have somehow a pipelined execution of this algorithm. And now the next robot would do the same, so it swaps this vector 1 along the chain. So it moves in distance 1 to its neighbor, and so on. So from both sides, 2 vectors of length 1 are swapped towards the middle of the chain, and when they meet, this simply stops, and we have created 2 vectors of length 1 in the chain, and the next movement creates 2 new vectors, and so on, such that after O of n rounds, the line has the length of n minus 1. Okay, so this already concludes basically my talk. What have we seen today? We have seen that the max line formation problem is impossible to solve with circular viewing ranges, but we can do something with square viewing ranges. Then we have seen a converging algorithm for the OBLOT model, which converges in time n squared log n divided by epsilon. We could design a faster algorithm under luminous robots and the fully synchronous scheduler by these locally sequential movement. And for future work, we have 4 questions formulated. First of all, it would be interesting to know, is it possible to solve max line formation exactly in the OBLOT model? Because currently we can only converge. We conjecture it's impossible, but the proof is still open. We somehow are interested in general lower runtime bounds. So for example, can we reduce a factor of n squared to a factor of n in the OBLOT algorithm? Is that possible or not? Is it possible to design a linear time algorithm with luminous robots in the semi-synchronous scheduler? That would also be interesting. And lastly, the impossibility result we have shown only holds for the OBLOT model. And the question would be, is it possible to solve max line formation with circular viewing ranges by considering luminous robots? And these 4 questions would shed some light about this max line formation problem, which are left for your future research. This concludes my talk. I want to thank you for your attention, and let's have a discussion about this at the conference. Bye.